Water is a potential source of clean energy due to its abundance on Earth. The inherent capacity of water can be harnessed and converted into electricity. Various technologies exist to convert the kinetic and potential energy of water into usable electrical power. Harnessing water's energy potential offers a sustainable alternative to fossil fuels. Water-based energy solutions can significantly reduce carbon footprints and promote environmental sustainability. Hydroelectric power generation relies on converting the potential energy of stored water into kinetic energy. Water stored at a height possesses potential energy due to gravity. As water flows downwards, potential energy is converted into kinetic energy. The kinetic energy of the flowing water drives turbines to generate electricity. Hydroelectric power plants efficiently harness the energy of water to produce electricity. Hydroelectric power harnesses the energy of flowing water to generate electricity. The kinetic energy of the water turns the blades of a turbine. The turbine is mechanically connected to a generator. The generator converts mechanical energy into electrical energy through electromagnetic induction. Electrical energy is then transmitted to the power grid. Hydroelectric power provides a renewable and sustainable source of electricity. Hydroelectric generators convert mechanical energy from rotating turbines into electrical energy. The turbine's rotation spins magnets within coils of wire inside the generator. This spinning motion induces an electric current in the coils of wire. The strength of the induced current is proportional to the speed of rotation and the strength of the magnets. The generated electricity is then transmitted through power lines to homes and businesses. Hydroelectric power provides a renewable and sustainable source of electricity. Hydroelectric power plants generate electricity, which is then transmitted over long distances. High-voltage transmission lines efficiently carry electricity from the power plant to substations. Substations reduce the voltage of electricity for distribution to homes and industries. Electricity powers homes and industries, lighting up cities and enabling modern life. Electrolysis is a method to derive energy from water. Water molecules, H2O, consist of 2 hydrogen atoms and 1 oxygen atom. Electrolysis uses electrical current to split water molecules into hydrogen and oxygen. The separated hydrogen can be collected and used as a clean energy source. An electrolytic cell is used to perform electrolysis, which requires an external power source. The electrolytic cell contains 2 electrodes, an anode and a cathode. Water within the electrolytic cell acts as the electrolyte, facilitating ion transport between electrodes. The anode is the electrode where oxidation occurs, while reduction takes place at the cathode. The power source provides the electrical energy needed to drive the non-spontaneous electrolysis reaction. Electrolysis involves using an electric current to drive a non-spontaneous chemical reaction. In water electrolysis, the electric current causes water molecules, H2O, to dissociate. Water molecules split into positively charged hydrogen ions, H+, and negatively charged hydroxide ions, O. Hydrogen ions, H+, migrate towards the cathode, while hydroxide ions, OH, move towards the anode. Electrolysis involves the movement of ions to oppositely charged electrodes. Hydrogen ions, H+, are positively charged and migrate towards the cathode. Hydroxide ions, OH, are negatively charged and migrate towards the anode. At the cathode, hydrogen ions gain electrons to form hydrogen gas. At the anode, hydroxide ions lose electrons to form oxygen, gas, and water. The overall process results in the decomposition of water into hydrogen and oxygen gases. Electrolysis involves using electrical current to drive a non-spontaneous chemical reaction. At the cathode, reduction occurs, leading to the formation of hydrogen gas, H2. At the anode, oxidation occurs, resulting in the formation of oxygen gas, O2. The overall electrolysis process produces hydrogen gas at the cathode and oxygen gas at the anode. Hydrogen gas is collected in a separate container The collection process highlights hydrogen's potential as a fuel source. Collected hydrogen can be stored for later use as a clean energy source. Hydrogen gas separation and collection is a key step in harnessing its energy potential. The purity of collected hydrogen is critical for efficient fuel cell operation. A fuel cell converts the chemical energy of hydrogen into electricity. Hydrogen gas is supplied to the anode, where it is oxidized, releasing electrons. Electrons flow through an external circuit, generating electricity. Oxygen is supplied to the cathode, where it combines with electrons and protons to form water. The only byproduct of this process is water, making it a clean energy technology. This completes the energy conversion cycle, producing electricity and water from hydrogen. A fuel cell generates electricity through a chemical reaction between hydrogen and oxygen. Hydrogen atoms are split into protons and electrons at the anode. Electrons flow through an external circuit, creating an electrical current. At the cathode, oxygen, protons, and electrons combine to form water as a byproduct. Electrolysis can be harnessed to produce hydrogen, which then fuels a hydrogen fuel cell. The hydrogen fuel cell converts the chemical energy of hydrogen into electrical energy. The electricity generated from the hydrogen fuel cell is then used to power a light bulb. This demonstrates a practical application of electrolysis for generating clean energy and powering devices. Hydroelectric power generation involves energy conversion from water potential to electricity, incurring losses at each stage. Energy losses in hydroelectric systems occur due to turbine inefficiency, friction, and electrical resistance. Electrolysis, the process of splitting water into hydrogen and oxygen, also experiences energy conversion losses. Electrolysis efficiency is affected by factors such as electrode material, electrolyte concentration, and operating temperature. Both hydroelectric and electrolysis processes involve multiple energy conversion steps, each contributing to overall efficiency reduction. Minimizing energy conversion losses is crucial for improving the overall efficiency and sustainability of both hydroelectric and electrolysis technologies. Water represents a significant, sustainable, and renewable energy source. Hydroelectric power harnesses the energy of flowing water to generate electricity. Tidal energy utilizes the natural rise and fall of tides to produce power. Continued research and development are crucial for advancing water-based energy technologies. Investing in water energy technologies can lead to a cleaner and more sustainable energy future.